The mean value theorem. Let's talk about what the mean value theorem is talking about. If y equals f at x is continuous at every point on a closed interval a to b, so we know we need to have a continuous function. And it's also got to be differentiable at every point. So we got some conditions here. We got to be differentiable and continuous on the interior points. Then there must be at least one point, c, in a, b, at which f prime at c equals f at b minus f at a over b minus a. Listen, I really love the mean value theorem, and it's not because of the definition you see here. It's because this looks completely wild, what's going on here. But when you really find out what mean value theorem is all about, it is so intuitive. I won't say obvious, that's not true, but it's so intuitive once you really see what it's talking about. So before you overjudge this opening definition, check out the diagram that's coming that I think really crystallizes what's happening here. So, in words, there's at least one point that we will find that the tangent slope is equal to the secant slope from b to a. There is at least one point in AB where the instantaneous rate of change is equal to the average rate of change from A to B. Well, even that, I don't know that those thought bubbles really cleared up, but the picture really will. And after seeing this picture that's coming up here, you can go back to these definitions and they will really become clear. So say you're going from some A value over to some B value. And if you find the slope between those 2 points, and this is the average rate of change, so a secant slope, so you just find the slope between those 2 points, and that's the right side of the equation you're seeing above, f at b minus f at a over b minus a. So if you find that secant slope, what the mean value theorem says, there's that slope. Ooh, we're going to add a little something there. Let's just get the pen to the color I want here. Yeah. That slope of that secant line is f at b minus f at a over b minus a. And what the mean value theorem says is somewhere between a and b, there'll be this point c, and finding it, we'll talk about finding it in a minute. Don't worry about finding it. This is an existence theorem. It says it exists. Somewhere in there, there'll be a point c where the tangent slope at that c will be exactly the same as that average, as that secant slope you got there. Now, what's intuitive about this is if you look at the picture at A there, right at that initial point that they're talking about there, and in this picture, the instantaneous rate of change happens to be negative there. But the important thing is that slope happens to be less than the secant slope. And what the mean value theorem is saying is that at some point, if you start off less than the average slope, you're going to have to eventually go to more than the average slope. If that slope's going to be the average and you're starting less than, at some point you're going to have to be more. So like in here, the slope was less, and so over here somewhere it's got to be more. Well, if it's got to go from less to more, at some point it's got to be equal. If you're going to go below it and then above it, at some point you've got to hit some point where it happens to be equal. And that's what the theorem says, is that f prime at c, the instantaneous rate of change up here at some value along the way will be equal to the average rate of change over the whole interval. Now, this only works if it's continuous and differentiable. We'll talk about how this theorem can fall apart if it's not continuous or not differentiable, because you might be thinking of some examples in your head where it's like, well, it wouldn't work for this or wouldn't work for that. Well, yeah, there's situations where it won't work. Those are the situations where it's not continuous or not differentiable. So here it is again, the statement. If y equals f at x is continuous at every point on the closed interval and is differentiable at every point in the interior, then there's at least one point where c in the interval a to b at which the instantaneous rate of change at that particular value will be equal to the average rate of change over that whole section. And where does it really come from? It really comes from, well, if you start off less than that average rate of change, you're going to have to go more at some point. So you're going to have to hit the slope at some point. And if this diagram doesn't show, but if you start off with a higher slope, a higher instantaneous rate of change than the average rate of change over the interval, well, you're going to have to come back down again, and you're going to have to go lower at some point than the average rate of change. So that means you're going to have to exactly hit the average rate of change at some point. So here's an example to sort of bring all that together. They say, okay, show that this function here satisfies the mean value theorem on the interval 0, 2. Now, okay, so this function, we can just look at it. We know cubic polynomials are continuous everywhere and differentiable everywhere, so we don't have any problems there. So we don't have to spend our time worrying about that, whether the mean value theorem, whether the conditions are met, because they are met here. So we want to prove that it works here. And I've made a separate page in here to do that. Here it is. Here's the example again. Show that this function satisfies the mean value theorem on the interval 0, 2. So what I'm going to find is the average rate of change on the interval that they're talking about. What I'm really finding is the slope of the secant on the interval they're talking about. So I just want to find f at 2. F at 2 minus f at 0 over 2 minus 0. And if I put 2 into my calculator into that whole function, what I get is -1. And I put 0 in there, I get a -7. Be careful with the negatives there. I got to subtract a negative there. So I get over 2 minus 0. So I get -1 minus -7 would be 6. Bottom's 2, so I get 3. So that average rate of change over that interval is 3. So what they're saying, I'm going to draw just a little tiny diagram over here, is that over that interval, the slope of the secant is 3. And the mean value theorem says that at some point, at least one point, between 0 and 2, we should find that the instantaneous rate of change is 3. So let's find where that point is. Now, f prime at x is 3x squared minus 6x plus 5. And we want to set f prime at x equal to that 3 that we're looking for. So 3 equals 3x squared minus 6x plus 5. And so I get 0 equals 3x squared minus 6x plus 2. And so I'm going to solve this quadratic, and I can see it doesn't factor, so I'm going to have to use the quadratic formula. But I want to tell you before I do that what's implied by the mean value theorem. And the mean value theorem says that I'm going to find x values. Okay, I know I'm going to find x values here. But what I'm going to find is, with those x values, that one of these x values is going to be between the 0 and 2. Somewhere it's going to hit the right tangent slope of 3 between 0 and 2. So if I go through the quadratic formula here and I go x equals -b plus or minus square root b squared minus 4ac all over 2a. So I get x equals a 6 plus or minus, okay, I know it's -6 squared, but that's the same as 6 squared, so I'll just put that in there, minus 4 times 3 times 2 all over 2 times 3. And if you put those into your calculator, what you'll get is the first x value of 1.58. As predicted, is that somewhere between 0 and 2. Now, what's interesting here is in this particular case, I find the other one, 0.42, is also in that interval between 0 and 2. So it did it twice that I found that slope came out to 3. But it doesn't have to do it twice. The mean value theorem says it's going to happen at least once. So there. Therefore, f prime at 1.58 equals 3. So the mean value theorem, we often see this shortcut, the short form of this as MVT there, is satisfied on the interval 0, 2. Okay? So that's sort of using the mean value theorem. We knew it was going to be there, and we used that to double check that it was there. Okay, so mean value theorem for derivatives. Okay, that was the same. We want to talk about a little more about the continuity part and the differential part. These were important qualifications of the mean value theorem, that we should see the function is continuous and differentiable. So what happens if those things don't happen? So this graph shows what could happen here. And if you look at the first graph there, what you see is that between a and b, the slope would be 0 in that section there. And clearly, the slope of that graph will never be 0 in there because it's not differentiable there. So right there at that value right there, x equals 0, we don't get a, it's not differentiable, so that's why it fails. Next is the graph of int x, and they don't show the whole graph here. They just show int x, and it jumps here, so it's discontinuous. And you can see that the slope of int x is always 1 or doesn't exist. And here, that slope between a and b would be slope of 1, and we're never going to get that slope in between there. And why does it fail? It fails because both of these functions, one's not differentiable. It happens to be not differentiable right there at x equals 0, and this one happens to be, well, discontinuous at x equals 2. It's also not differentiable there, but it's not continuous there. So here's an example. Create two functions that fail to satisfy the mean value theorem on the interval -1, 2 for different reasons. So again, I made myself some room here to answer that. I want it to fail on -1, 2. So I could first come up with one that was not differentiable. Also not continuous, but those two things often travel together. So I can make up a function like f at x equals x minus 7 over x. So with a vertical asymptote at x equals 0. So that's between -1 and 2. So it's not going to satisfy the conditions of the mean value theorem. And then I could go with f at x equals absolute value of x, which is, the absolute value function. And the absolute value function isn't differentiable at x equals 0. So that would also not do it here. So I guess over here, this one is not continuous is really the big thing. And usually when it's not continuous, you get not differentiable as well. But so these were two different reasons why that happened. Okay, so some results from the mean value theorem. Some other things that immediately follow from the mean value theorem are some information about increasing and decreasing functions. And if you've never seen the word corollary before, corollary is a result that follows from another theorem with very little proof. So we've got the mean value theorem in our hand, and we immediately get these corollaries. So this first one is let f be continuous and differentiable. Then if f prime at 0 if f prime is greater than 0 at each point on AB, then f increases on AB. This may seem so obvious. I mean, it is sort of obvious. If the derivative is greater than 0 on every value in an interval, well, of course, it's going to be increasing. And if f prime is less than 0, then, of course, it's going to be decreasing. Like if f prime is less than 0 at each point in AB, then, of course, it's going to be a decreasing functions. We sort of took that as given before. We just sort of said, well, that makes perfect sense to me. But here's a little proof of it, and the proof says, let x1 and x2 be any 2 points on AB with x1 less than x2, and often it's helpful to draw yourself a little picture here to go, okay, well, I've got an x1 and an x2, and x1 smaller than x2. So if you then take the mean value theorem and say, okay, well, we'll just rearrange it, we get that f at x2 minus f at x1, that is, the difference in the y values between these 2 points will be f prime at c times x2 minus x1 for some value between c between x1 and x2. And so the sign of the right side of this equation is the sign, same as the sign of f prime at c, because this is positive. x2 minus x1, this part here, that's got to be positive because x2 is greater than x1. That was what we started with, was an x1 and x2. So the sign here will be decided by the sign of the derivative here. And so if the sign of the derivative is greater than 0, then what we get is that the right-hand side will be positive, and that means f at x2 has to be the bigger one. That's the part A of the theorem. And if f prime at c is less than 0, so we get negative on the right side, that means that we must get negative on the left-hand side, and so that means that f at x1 would be the greater one there. So that just follows like almost automatically from the mean value theorem. Corollary number 2. Another fact that we just sort of have used before, we never really proved it before, but the mean value theorem nicely proves it. Functions with f prime equal to 0 are constant. If f prime at x equals 0 at each point on an interval, then there is some constant where f at x equals c for all the x values in that interval. So what we want to prove is that in the interval, every f at x1 is equal to f at x2, no matter what x1 and x2 you select. So no matter where you go in the interval, and I really like this little picture here to really crystallize what we're talking about. If we look at an x1 and an x2, we're always going to find that their y values will be equal if the derivative is 0. And that may seem obvious, but the mean value theorem proves it nicely algebraically. We can assume that the points are numbered so that x1 is less than x2. Since f is differentiable at every point, it is also continuous. I mean, once you say it's differentiable, you've already said it's continuous. It's got to be continuous there. Thus, f satisfies the hypothesis of the mean value theorem. So we know that f prime at c is equal to f at x2 minus f at x1 over x2 minus x1. That's just a statement of the mean value theorem. But because f prime at c is always equal to 0, that was what was said in the corollary, is that we know this is equal to 0. That means the right side has to equal to 0, and the only way for that to happen is for f at x1 to be equal to f at x2. You know, pretty obvious proof, I think. And the last corollary there is functions with the same derivative differ by a constant. If you find that two functions have the same derivative, then there must be a constant so that f at x and g at x are the same function and they only differ by a constant. So how do we prove that? Well, we make up a new function, h equals f minus g. And for each point in h, then we can find its derivative. H prime will be f prime minus g prime. But we know that f prime is equal to g prime. That was the statement in the corollary. So that means that h prime must be 0. And then we know that if h prime equals to 0, from corollary 2 up at the top there, if we know the derivative is 0 all the way along the way, we know that h then must be some constant function. And so going back to our original statement that h at x equals f at x minus g at x, equals, we now know has to equal c, then we know that we can just take this part and say, okay, then f at x equals g at x plus c. And we come up with what might seem like a pretty obvious result. If two functions have the same derivative, then they must only differ by a constant. So here's an example that we want to use. Find a function whose derivative is f at x equals 6x squared minus 3x plus 5, and whose graph passes through this point. So what we want to do is, basically what we want to do is find what we call the antiderivative. We want to say, okay, well, we want to come up with some function whose derivative is the function up there. And often we use capital F to indicate a function that has to be derived to get the original function. And so to find that out, we just got to think this through a little bit. Okay, if we want to come up with 6x squared, then we're going to need something cubed to get back to that derivative. So maybe like a 2x cubed, that derivative would be 6x squared. And then if we want the derivative to be 3x, then I guess we'll need like 3 halves x squared, just sort of playing with the coefficients there. And then if we want a derivative of 5, we'll need a last term of 5x. Now, the thing is, though, there are many functions who have that derivative. That is, all of the functions that have the derivative 6x squared minus 3x plus 5 will start with 2x cubed minus 3 half x squared plus 5x. They'll all start like that, but then each one will have a constant at the end, some number out there that when we take its derivative, it's 0, and we don't know what that constant is. Fortunately, in this question, they give us some information, so we go when x equals 2, the function will be equal to 13, so I get 13 equals 2, and I put this 2 in there, 2 cubed minus 3 halves, 2 squared plus 5 times 2 plus c. And then, like we've been doing all the way along in questions like this, that subbing allows us to quickly come up with the value of c, and I think if you manipulate around, you'll find that c is negative 7. So the function that works here is 2x cubed minus 3 halves x squared plus 5x minus 7. If that seems weird at all, just take the derivative of that function and watch what you get. You'll get that original function back. And then this just takes some practice to get those antiderivatives, they're called. So, I did that example on the previous page there. So that example's on this page again. I split that out so I could do that work. So, antiderivative. A function f at x is an antiderivative of f at x if the derivative of your capital F function is the original function for all x. The process of finding an antiderivative is called antidifferentiation. So, if a function has one antiderivative, it has an infinite number of antiderivatives. We can always add a constant there. So here's some more examples to do. We want to find two antiderivatives of this function, and we want to do something with some physics, of course. We always seems to come back to physics here. So I've split those out. So here's those examples again. find two antiderivatives of this function. So f of x equal to sine 3x minus 2e to the x. So to find that antiderivative, I'm going to go with capital F. We often do that to say, okay, here's an antiderivative of this. So sine 3x, okay, so to get to sine 3x, I must start with cos of 3x, because the derivative of cos 3x is negative sine 3x. Oh, okay, so a negative pops out, so I'll need a negative out here. And then due to chain rule, negative cos 3x is going to get multiplied by 3, so I'm going to need a 1/3 out there to multiply with the 3 to end up with a 1 out front. And if that doesn't make sense when you look at it, well, take its derivative, and you'll see, okay, that works. And then to get 2e to the x, well, okay, I'll just need 2e to the x. E to the x is very nice with these kind of derivatives and antiderivatives, because the derivative of e to the x is e to the x. But then I could have a constant out here. So here's my two answers. Find two antiderivatives. I could have f of x equals negative 1/3 cos 3x minus 2e to the x plus 1, so any constant I want out there. Or maybe I could have like a g at x equals negative 1/3 cos 3x minus 2e to the x. Got to have all that stuff the same, and then say like a plus 10, any constant I want out there. And if you have any doubts about that, take the derivative of both those capital letter functions I've done there, f and g, and you'll find you get the original function back. And that it's really instructive to do that, to find that derivative and go, oh, I see. When I take the derivative of those things, I end up with the original function. So to find antiderivatives, I'm just playing around with those coefficients and those functions to get something that's going to come out as the right derivative. Okay, last example. An object is thrown downward from a height of 10 meters. If the acceleration due to gravity is 9.8 meters per second, find the equation, an equation for the object's height above the ground. So what I do know is that the acceleration is negative 9.8. I say negative because it's downwards. The acceleration due to gravity is downwards. So then to find velocity, well, I've got this new antiderivative weapon available to me where I can say, okay, if I want to find the velocity, what I need is an equation that its derivative will be that negative 9.8. So it's negative 9.8t plus some constant. So that'll be the velocity function. Now, in this particular question, I'm going to get all touchy about the physics here, but it says thrown downwards, not dropped. See, if it had said dropped, then I would have known that the initial velocity was 0. But it didn't say that. So there's some initial velocity that it got thrown down at. So what I'm going to say here is that when t equals 0, the velocity is equal to some v naught that they didn't tell me in this question. So I'm sort of stuck with this v naught. But I can sub that in and say, okay, so the velocity at 0 is v naught. And when I put in 0 there, I find that this constant that we're talking about in this physics question here, the constant is the initial velocity. So we have, a little more formally, the velocity function will be negative 9.8t plus some initial velocity that they didn't tell me in this question. And, some people might look at that and say thrown downwards, it starts off at rest or something like that. But I think it sort of implies when it says thrown downward that there was some initial velocity here. We try to say dropped if it's just dropped from with no initial velocity. So that's the velocity function. But it wants an equation for height. So I've got to do this antiderivative move again. That is, I want to come up with a height function that when I take its derivative, I find this velocity function I've already got. So I got to do this antiderivative procedure again. I got to say, okay, what function should I have started with that would have came out to the right velocity here? And so, well, to come out to t, I guess I need a t squared. That 2 is going to multiply by whatever I got out front to get negative 9.8. So I guess I need a negative 4.9 there. And then the v naught, we'll have to have a t there because the derivative of v naught t would just be the v naught. Just think of the v naught as like, maybe it's like a 20 or like a 50. It's just some number. And then I get some new constant here. And you got to be careful with constants sometimes. Like this constant over here, maybe I'll just call it C1 and I'll call this one C2 because they're not necessarily the same constant. But here I can solve for that constant because they did tell me that when t equals 0, the height equals 10. So I can sub in the 10 over there. This will be 0, this will be 0, and that constant, that second constant is 10. So therefore, the height is negative 4.9 t squared plus v naught t plus 10. And if any doubts at all about what that all means, take that derivative twice and see what you get, because what you're going to find is you get those velocity and acceleration equations back. And it's very instructive on how I came up with those, maybe so quickly, but honestly, it's not that big a deal what I did. I just sort of played with the coefficients and so on. So don't overthink that too much. It just takes a little practice. And as you go through these, always take the derivatives to go backwards to go, did I choose the right coefficients? Did I choose the right functions? All right. That's it. Mean value theorem with a little extra stuff there for you on how to do a little bit of antiderivative type stuff. Have a great day.